Hi friend, welcome all to my educational channel Math A to Z. This is the third class of the power series solution of ordinary differential equation. In this class, we discuss the method of power series solution of second order ordinary differential equation about the regular singular point. Now go to the method. Here we take an ordinary differential equation of second order which is linear also, and in normalized form d2y by dx2 plus q of x into dy dx plus q of x into y equal to 0. This is 1. And let x equal to x0 be the regular singular point. Hence, from the singular point, definition of singular point, regular singular point, we say that x minus x0 into p of x and x minus x0 whole square into q of x must be analytic at x equal to x0. Now we write the equation 1 as x minus multiplying both sides by x minus x0 whole square, both sides multiply with x minus x0 square. So we can write x minus x0 square into d2y by dx2 plus x minus x0 into p of x, and here extra x minus x0 is here, x minus x0 into dy dx plus x minus x0 whole square into q of x into y equal to 0. This is 2. Now since x0 be the regular singular point, so here we say that this and this must be analytic at x equal to x0. That is, this and this must be derivable at x equal to x0 and derivable also in the neighborhood of x equal to x0. So we can write x minus x0 into p of x and x minus x0 whole square into q of x in the form as, in polynomial form. X minus x0 into p of x equal to, let p0 plus p1 into x minus x0, p2 into x minus x0 whole square plus 2 pn x minus x0 whole to the power n to infinity. This is named as 3, and x minus x0 whole square into q of x equal to q0 plus q1 into x minus x0 plus q2 into x minus x0 whole square plus qn into x minus x0 whole to the power n to infinity. This is 4. Now let the solution of 2, this solution of 2 as y equal to summation n equal to 0 to infinity a0 into x minus x0 whole to the power m plus n. This is named as 5. Here this is very important to remember. About the ordinary point, we take the solution y equal to summation n equal to 0 to infinity a0 into x minus x0 to the power n. But when we have to find the solution about the singular point or regular singular point, then we must assume the solution as, this is m plus n. Okay, here extra term is m. We find from 5 dy by dx, first derivative, and d2y by dx2, that is second derivative, and here is also we assume, and we put y dy dx and d2y by dx2 in equation 2, this equation, and we get the result as, here we put the value of d2y by dx2, that is summation n equal to 0 to infinity m plus n into m plus n minus 1 into a0 x minus x0 whole to the power m plus n minus 2. We get this into this and we expand this series for n equal to 0, n equal to 0 to infinity, and we get as put n equal to 0, then from here the first term is m into m minus 1 into a0 into x minus x0 to the power n minus 2, and here also x minus x0 whole square. Then we get the first term as a0 m minus 1 into x minus x0 whole to the power n. Putting n equal to infinity, putting n equal to 1, we get the second term and so on, and this is also the infinite series. Now we put the value of x minus x0 into p of x. X minus x0 into p of x, that is from 3. Here we write x minus x0 into p of x, and we multiply dy by dx first by x minus x0, then we get the value of x minus x0 into dy dx, and this value put in here, this. Also x minus x0 whole square into q of x, this is x minus x0 into q of x in 4, this is q0 plus q1 x minus x0 plus q2 x minus x0 whole square to infinity, and this value put here. At last we put the value of y, that is a0 here y, this is a0 into x minus x0 to the power m, a1 into x minus x0 to the power m plus 1 to infinity. Okay, and the name of this relation is 6. Now equating the coefficient of x to the power m, equating the coefficient of x minus x0 to the power m, x minus x0 to the power m plus 1 and x minus x0 to the power m plus n from both sides of 6, and we get the relation as, we get x minus x0 to the power m, here the coefficient of x minus x0 to the power m is a0 m minus 1, we write here, and when we multiply p0 with a0 m x minus x0 to the power m, we also get x minus x0 to the power m. So this is p0 a0 m, here we write p0 a0 p0 m a0. Also we get x minus x0 to the power m here, that is q0 into a0, and we taking common a0, so we get the coefficient of x minus x0 to the power m, this is a0 into m minus 1 plus p0 into m plus q0, and right side is 0 obviously, so this is 0, and the name is 7. Similarly, we consider the coefficient of x minus x0 to the power m plus 1. Here the first coefficient is this a1 into m plus 1 into m, we write here, and from the second term we get p0 into a1 into m plus 1, here we write p0 into a1 into m plus 1, and from the last term q0 into a1 into x minus x0 to the power m plus 1, that is q0 into a1. Also we get another two coefficient, this p1 into x minus x0 into a0 m x minus x0 to the power m, that is x minus x0 to the power m plus 1. So the coefficient is p1 a0 m, p1 a0 m, and here similarly q1 into a0, q1 into a0, there is also x minus x0 to the power m plus 1. So the sum is also equal to 0. This is 8. Similarly, we consider the coefficient of x minus x0 to the power m plus n. And here from the first term or first line, we get the coefficient is m plus n into m plus n minus 1, we write here. And from these two parts, this and this, we get infinitely many members whose coefficient are x to the power m plus n, and we write this as to infinity. And after the first term, second, third, fourth to infinity, we can write all the term after the first as a summation, as k equal to 0 to infinity a n minus k into pk m plus n minus k plus qk equal to 0. This is 9. In series solution, we know that the first coefficient a0 must not be 0. So we say that m into m minus 1 plus p0 m plus q is equal to 0 from 7. And this equation, name of this equation is 10. This equation is called indicial equation. Indicial equation of the differential equation. Okay. So from indicial equation, this is a quadratic equation of m. We get two value of m, and from the relation 8 we get a1 by a0. We write here a1 by a0 as minus p1m plus q1 by m plus 1 into n plus p0 m plus 1 into q0. And this is obviously a function of m, and we assume this function as f1m, the function of m. Now using this value and using this relation for a particular value of n, we get in similar way, we get a2 by a0 as f2m, a3 by a0 is equal to f3m, and so on. Okay, from this relation and using this relation, by putting particular value of n, we get all the value a2 by a0, a3 by a0, a4 by a0, and so on. Now from the solution y, we get from the solution y equal to summation n x minus x0 to the power m plus n, we get by expanding a0 plus a1 into x minus x0 to the power m plus 1, a2 into x minus x0 to the power m plus 2, a3 into x minus x0 to the power m plus 3 to infinity. Now taking common a0, we get 1 plus a1 by a0 into x minus x0 to the power m plus 1. Here also a mistake, a0 into x minus x0 to the power m. Okay, and taking common a0 into x minus x0 to the power m. Now this is 1 plus a2 by a0 into x minus x0 to the power 2, a3 by a0 x minus x0 to the power 3 to infinity. This is the solution. Now here we put a1 by a0 as f1m, a2 by a0 as f2m, A3 by A0 as F3M and so on. Okay, and we name this as E11. Now here three cases may arise depending upon the value of m from the initial equation. What are three cases? The three cases are: case 1, when two values of m are distinct and not differ by an integer. We let m1 and m2 are two distinct values of m, where m1 minus m2 does not belongs to capital M, that is not differ by an integer. We already see that the solution is of the form a0 into x minus x0 to the power m, 1 plus f1 m x minus x0 plus f2m x minus x0 whole square to infinity. Here we put m equal to m1. We get one independent solution of the given differential equation 1. Also we put m equal to m2. We get the second or another independent solution of the given differential equation, and then we add these two independent solutions like this: y equal to a into this, when first we put m equal to m1, and b into x minus x0 to the power m2, that is we put m equal to m2 in this relation, and we add a into u type, au plus b. Here we get u by putting m equal to m1, and we get v by putting m equal to m2, and we changing the arbitrary constant a0. For one time is a and for second time is b, where a and b are the arbitrary constant. This is the first case. Here we let two value of m are equal, which are both m1, this, and the general solution in this case is y equal to a into w at m equal to m1 plus b into del w by del m at m equal to m1, where a and b are obviously arbitrary constant. And what is w? W is the same as above y. W is x minus x0 to the power m into 1 plus f1m into x minus x0 plus f2m x minus x0 whole square to infinity. Okay, here we put m equal to m1, we get this value, and we differentiate partially with respect to m, that is dw by dm, then we get this value. Now put m equal to m1, we get this result. Okay, this is the case 2. And now the case 3 is when two values of m are distinct and differ by an integer. That is, let m equal to m1 and m2 are two values of m, and m2 greater than m1, that is m2 is greater value of m. Then we get one independent solution by putting m equal to m2, that is the greater value of m, in w. The w is given in case 2, and to get the other independent solution, here two cases arise. That is, the first independent solution we get by putting m equal to m2, and for the second independent solution we get two cases. In first case, that is case A, if for m equal to m1, that is the smaller value of m, if we get the independent solution, then we get the complete solution of the given differential equation as in case 1. case 1, that is y equal to a into w, m equal to m1, and b into w, m equal to m2. This is similar as case 1. Now, if m equal to m1, that is the smaller value of m, does not gives the independent or does not gives the other independent solution of the differential equation, then we go to the case B. In case B, if m equal to m1, that is the smaller value of m, does not give independent solution, or if a factor m minus m1 is present in the denominator of the constant coefficient Cn starting from some finite term, that is in the W, in W we get C2 by m minus m1, okay, m minus m1 into x minus x0 whole to the power 2 plus C3 m minus m1 into x minus x0 whole cube, and so on in this case. So if m equal to m1 does not gives any independent solution, or here if this case arises, then the solution of the equation can be written as y equal to a into w at m equal to m2 and b into w1 by del m at m equal to m1. What is w1? W1 is nothing but m minus m1 into w. Okay, we first multiply m minus m1 with w, then we differentiate with respect to, or partially differentiate with respect to m, then we get the second term, and this is the case B to get the general solution of the differential equation. And we give one or two examples for both the case in next classes. Okay, so stay with me. Thank you for watching. This is the today's class.